Now, based on what we've seen, we should notice that there's one part of this phased lock loop that is non-linear. And so this is going to make things harder, right? Because on almost everything that we've done, when we do the analysis of how the various systems are going to work, we've almost always assumed that it was going to be linear. But this is a non-linear process. So we're going to have to find a way to deal with this if we want to analyze this. So one of the best ways to do this is to use the small angle approximation. And the small angle approximation basically says that the sine of an angle is approximately equal to the angle. And so if you just look at this, you can find this on Wikipedia, but you can see we're going to be comparing the red line and the green line, so these two lines right here. And we can see that for 0.5 radians, there's only about 4% error in this approximation. And for your reference, right, 0.5 radians is about 30 degrees. So up to even 30 degrees, right, you could approximate this as a linear system where just this is equal to this. So we can approximate this as a linear system for that small range. Okay, so if we were to do this, make this small error assumption, we can simplify this into the time domain where we have a summer, so some way of comparing the received input phase and the VCO output phase, and comparing them and making an error, passing them through a loop filter, getting an output that then goes back in to the VCO, which integrates in time. Now, if you go and look at a table of Laplace transforms, we can put this into the S domain for more simple analysis. So we can quickly find, this one is in the Electric Circuits by Nilsson and Rydell, pretty popular book, but this type of table is in many books. We can see that a model for a time integral would be 1 over S, and whereas a simple function, right, would just be, you'd take f of t and turn it into f of s. So doing that here, right, we just took h of t and turned it into h of s, and this integral, right, this time integral turns into a 1 over s. So now we have an S domain system that we can analyze. So if we were to look at the output over the input in the S domain, we can then arrive at this. And this is basically a straightforward feedback analysis. If you go and look in a control systems textbook, you'll see this. I'm not going to cover it in more detail, but this is just how this works. Then if you want to transform this into a more commonly seen system, we could multiply by 1 over 1 and then arrive at something that looks like this, where we have the output over input in the S domain. So this is basically a simple feedback analysis, and you could find the methods to do this in various control systems textbooks. So in the S domain, we can do the same definition. We can define the error in the S domain, just like we define the error in the time domain, where it's the difference between the input and the output. And so if we were to multiply, if we were going to take this expression for the error, multiply it by 1 over 1, right, use this as 1 over 1, and then rearrange this, right, because in the previous videos, right, we found what the out over the in is, so this kind of makes sense to move towards this model. We can rearrange it. Now we have this out over in, and we found a definition for this previously, right, using our feedback analysis, and then we can pull this out, and now we know this from our feedback analysis, and we have basically rearranged our error function to find this. So from feedback analysis, we found this, and we can put this into here, and now we have a new expression for error in the S domain. So then if we see this, though, this is not quite yet in what would be considered a standard form for the S domain error. And so, right, we often put these in a standard form that's easy to move back and forth between using Laplace transform. So let's try to see if we can put this into a standard form. So this is our new expression for error. We're going to do some multiplication, basically, right, by 1 over 1, so take this denominator, multiply by 1 over 1. We're going to collect those terms together. Then we're going to simplify this into what would be considered a more standard form for an S-domain function.